Hi there, and welcome to this lesson on Pure Mathematics 3. And in this lesson, we're looking at how you can use logarithms to convert the graph of the exponential function, y equals ab to the power of x, into a straight line. Now, in the last lesson, we said that one important use of logarithms is to do exactly this, to convert an exponential function into a straight line. And having done that, to use our understanding of the gradient and y-intercept of a straight line to interpret the original function. There are two types of function that we've been looking at, and in this lesson, we're looking at functions of the form y equals ab to the power of x. And at first glance, that might look exactly the same as in the last lesson, but there is a crucial difference. X is the variable, and the variable is now the power in this exponential function, whereas previously we had ax to the power of b. A and b are constants that we need to calculate. So the theory, very similar as before. We start off with the equation y equals ab to the power of x, and then in order to convert it into a straight line, we take logs of both sides of the equation. So the left-hand side becomes the log of y, the right-hand side becomes the log of ab to the power of x. Using the rule for multiplying when you have logarithms, this can be split up into two parts, and you get the log of b to the x plus the log of a. Using the rule for powers, we can change this term into x log b plus log a. And just rearranging these two terms, we could write that as log y equals log b times by x plus log a. And the reason for doing that is because then you have the standard form of a straight line, where log y is the equivalent to y, m is the gradient, log b is a constant, that'll be the gradient of the line. In this instance, we still have x hasn't changed, and we do just use the values of x from the question when we do this. And log a will be the y-intercept of the straight line. The two axes, well, the x-axis stays as the x-axis, but the y-axis will become the log y-axis. And as we said, x and log y will become the two variables. We calculate values of x and log y. Values of x we don't need to calculate, they'll be given to us in the question, but values of log y we do need to calculate from the information that we're given. Then we plot those points on the graph and draw a straight line, joining them together, a line of best fit. We then use the straight line to estimate the y-intercept and the gradient of the line, and using those, we're able to calculate b and a in the original exponential function by using log b equals m, as we have up here, and log a is equal to c. Okay, things become a little bit more clear when you do an example. Now, I'll let you have a go at doing the example yourself first. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look at this. So we're given a table of values for T and R, where R is the radioactivity of a substance, measured, I think, in becquerels, over a certain number of days. We're asked to draw a linear graph in order to calculate the values of A and B in this original expression. And we're also asked to try and calculate the initial radioactivity of the substance. So that's the equation we've been given, R equals AB to the power of T, exactly as we did before. Take the log of both sides, split this up using the rule for multiplication, split this up using the rule for powers, and then you get the standard form for a straight line. Now, we've been given values of T and R. The values of T we will be using, but we need to calculate values of log R. So you'll need to add an extra row to the table and then calculate the values of log R. Once you've done that, we'll be plotting the values of T on the x-axis and the values of log R on the y-axis. So you'll need to choose a scale which is sensible, something like that would do, that makes sure that you can draw all the points and certainly that includes the y-axis, because we'll be needing to estimate the y-intercept. Plotting the points would give us something like that. Drawing a line of best fit will give us something like that. Now, from the graph, first thing we have to do is try and estimate as accurately as we can the y-intercept, and then we'll do the gradient. The y-intercept will be up here, and I did this more accurately on another occasion, and it's a tiny bit less than 2. Something like 1.95 will be the y-intercept up here. That means c equals 1.95. Now c is log a, so that means log a is 1.95. We need to find a. The way we do that, this is log to base 10, so we'll do 10 to the power of that and 10 to the power of 1.95. 10 to the power of log a, the 10 to the power of and the log cancel each other out, and that just gives us a equals 10 to the power of 1.95, which is about 89. Now the gradient, we can choose any 2 points that we like on the line. Doesn't matter which 2 you choose. Try and choose 2 that make life easy for you when you calculate the gradient. So I've chosen these 2 points because it looks to me as if that'll make life a little bit more straightforward. So a point here at 200, 0.2, and here at 100, 1.07. The gradient's the change in the y values divided by the change in the x values, which would be 0.2 take away 1.07 over 200 take away 100, which gives us minus 0.87 divided by 100, which is minus 0.0087. So that will be m, but m is log b, so therefore log b is equal to minus 0.0087. To solve that, we'd need to do 10 to the power of both sides. 10 to the power of log b gives us b, and here we've got 10 to the power of minus 0.0087, and pop that in the calculator. You'll get b equals 0.98. So what have we done? We started with this exponential function. We transformed it by taking logs into a straight line, and by doing that, we were able to calculate the values of a and b. So a is 89, b is 0.98. So the equation is r equals 89 times by 0.98 to the power of t. Now, if you remember in the question, we were asked to calculate the initial radiation. Well, the initial radiation is at t equals 0. So we just substitute t equals 0 into the equation, and that gives us 89 times by 0.98 to the power of 0, which is just 1. So that will give us about 89 becquerels. Okay, that is the end of the lesson. If you have the textbook, then turn to page 109. And in exercise 5D, questions 1, 4, 7, and 8 all deal with this type of exponential equation. Thank you very much for listening, and cheerio.